Here we have 5 consecutive even integers on the number line, p, q, r, s, and t, and we know their order. So we could actually already put on our number line 2, 2, 2, and 2 as the spaces among these tick marks. Now the question wants to know the average of this set, so I'm thinking, what would I need to know in order to answer that question? I'd need to know where this set is located on the number line, right? I mean, we could be on the negative side, we could be on the positive side, we could be in the hundreds, we could be in the millions. If I can kind of pinpoint where this set of 5 numbers lives on the number line, then I would be able to answer the question. So I'm looking for a statement to provide some kind of definitive value for one of the letters or even for some combination of those letters. And when I look at the statements, they each do provide something that would help me anchor the set of 5 numbers on the number line. In fact, if we think about this, statement 1 allows us to infer statement 2, because statement 1 helps us orient ourselves on the number line, and if we can do that, then we can really infer any values of any of the numbers, right? If we knew where one of those numbers is, we can figure out all the others. Same goes for statement 2. If we know statement 2, we could infer statement 1. So as I explain in section 2 of my book, which you can actually read for free on quantreasoning.com, when you have inferentially equivalent statements, meaning statement 1 implies statement 2 and statement 2 implies statement 1, you can already eliminate answer choices A, B, and C without even reading the question. And then if a statement is sufficient on its own, the answer is D, and if the statement isn't sufficient on its own, the answer is E. In this case, we can see that yes, each of the statements does help us orient ourselves on the number line. We would be able to tell exactly where P, Q, R, S, and T are. And I think about that, I mean, if we know that Q plus S is 24, well, where could these 5 numbers be? I mean, we know that the distance between Q and S is 4 on the number line, right? S is 4 units to the right of Q. If you were to move them up the number line, their sum would get bigger. If you move them down the number line, the sum would get smaller. So there can only be one place on the number line where Q and S could be if their sum is 24. Similarly with statement 2, right? So the average of Q and R is 11. Well, if you move Q and R up the number line, their average would get bigger. If you move Q and R down the number line, their average would get smaller. So there can only be one place on the number line where Q and R could be. So that's why I say that each of the statements does imply the other one. And in this case, the correct answer is D, because the statements they fully determine where the set of 5 numbers is on the number line, and we could figure out the answer if we wanted to. I'm not actually going to find the average of the set because this is data sufficiency. I don't need to find the average of the set. I just need to be confident that I could find it if I really wanted to. And again, each of these statements on its own fully determines where this set is on the number line, and the correct answer is D. If you found this video useful, go to quantreasoning.com for a lot more where that came from. You should also click that like button and let me know in the comments below what you'd like me to make future videos about. And of course, if you haven't yet subscribed, go ahead and do that and click that bell below so you get notified about future videos. See you next time.